Britain's freight railways are running out of time. The diesel fleet is aging past the point of no return. Barely 13% of routes carry overhead wires, and decarbonization deadlines are not moving. Into that gap arrives the Class 99, 8,000 horsepower, 6-powered axles, the most powerful standalone freight locomotive this country has ever operated. There's just one uncomfortable detail: Britain didn't build it. For nearly 2 centuries, Britain's railways stood as a symbol of industrial might and technical ingenuity. Steam giants like the LNER A4 Pacifics, built at Doncaster in the 1930s, once thundered across the country, their streamlined forms and powerful engines capturing the world's imagination. After nationalization, British workshops at Crewe, Swindon, and Derby churned out diesel and electric heavyweights, machines designed, assembled, and maintained by a homegrown workforce that numbered in the thousands. But by the mid-1990s, the last new heavy freight locomotive left a British assembly line. The closure of BRL's Crewe plant in 1990, followed by the end of new builds at Brush in 1995, marked the end of an era. Since then, not a single mainline freight locomotive of this scale has been built on British soil. A historian of industry puts it plainly: we went from exporting the world's most advanced locomotives to importing every heavy unit we now run. The reasons are layered: procurement policies that favored the lowest bidder, the collapse of domestic supply chains, and a shift toward off-the-shelf European designs. By the early 2000s, the workforce that once filled cavernous assembly halls had dwindled to a fraction of its former size. Today, Britain's most powerful freight locomotive arrives as a modified European platform, assembled abroad and tailored to fit the UK's unique loading gauges and operational quirks. The bicentenary of British railways now coincides with a moment of dependence. A nation that once led the world in locomotive engineering now relies on imported solutions to keep its freight moving. This paradox, heritage versus capability, hangs over the arrival of the Class 99, raising questions not just about power or emissions, but about what it means to sustain an industry and a legacy. At the heart of the Class 99's promise lies a fundamental engineering challenge: how to turn headline horsepower into actual pulling force, especially on Britain's unpredictable rails. The answer begins with the Coco wheel arrangement: 6 powered axles, each one driven by its own electric motor and inverter. This is not just a matter of brute strength. The real advantage comes from how the locomotive manages grip, or adhesion, between wheel and rail. A depot chief engineer explains that on a typical rainy morning, the difference between a train moving and one sitting stalled on a grade comes down to the physics of adhesion. Traditional locomotives, even powerful ones, often wasted energy in wheel slip, especially under heavy loads or on slick tracks. The Class 99 system takes a different approach. Sensors on every axle feed real-time data to a computer that calculates the precise torque each wheel can handle. If one axle senses the beginnings of a slip, a drop in friction, or a hint of lost contact, the system instantly trims power to that axle while maintaining drive on the others. This axle-by-axle control can boost usable tractive effort by up to 70% compared with older, fixed torque designs. The result is that the locomotive's 8,000 horsepower under the wires, or 2,400 from its diesel engine, is delivered in a way that sticks to the rails, not just in theory, but in the wet, leaf-coated reality of British freight lines. For operators, this translates directly into longer, heavier trains that can climb steeper gradients and keep to tighter schedules, regardless of weather. It is a leap in practical performance, rooted in the details of traction physics and made possible by digital control, an engineering edge that sets the Class 99 apart from its predecessors. A glance at the UK rail map tells the story. Only around 13% of the network used by freight trains is electrified. The rest, thousands of route kilometers, remains reliant on diesel, often through corridors where overhead wires have never been installed or where physical constraints make upgrades prohibitively expensive. For operators, this means a pure electric locomotive would spend most of its time idle, hemmed in by the limits of the infrastructure. On the other side, the backbone of the diesel fleet is showing its age. The average mainline freight locomotive in service today is more than 25 years old, with some units fast approaching their design life limits. Emissions standards have tightened sharply since these locomotives first rolled out, leaving operators facing a regulatory squeeze. A transport policy advisor describes the bind. You can't decarbonize with wires that don't exist, and you can't keep running 1990s diesels forever. The numbers back this up. With only a small share of the network electrified and an aging diesel fleet at risk of obsolescence, neither an all-electric nor an all-diesel approach can deliver the reliability, flexibility, or emissions cuts the sector now demands. The operational problem is clear: how to move heavy freight efficiently across a patchwork network without falling foul of environmental targets or stranding investments in aging hardware. A battery-heavy tri-mode locomotive promises a clean image, but the numbers tell a different story. To deliver just 30 kilometers of battery-only range, the minimum needed to bridge typical off-wire gaps on UK freight corridors, a tri-mode design demands a 20-ton lithium-ion pack. That extra weight is not trivial. It eats into payload, pushes axle loads to the limit, and can force speed or route restrictions on lines with tight clearances. Operators are then left with a choice: sacrifice capacity or risk breaching infrastructure limits. A procurement manager describes the dilemma. For every ton of battery we add, we lose a ton of freight or risk being barred from key routes. The cost is not just financial, it is operational. The batteries themselves require regular replacement every 12 to 15 years, and the supply chain for lithium and cobalt is anything but stable. Charging infrastructure at depots adds another layer of complexity, while the real-world carbon savings above buy mode are marginal, just 2% across a typical freight duty cycle. The buy mode Class 99, by contrast, carries a 3,000-liter tank ready for HVO, offering a 1,200-kilometer diesel range without the battery penalty. Its Stage 5 compliant engine meets the latest emissions standards, and HVO blends can cut carbon dioxide by up to 15%. The pragmatic calculus favors a BI mode solution: less weight, lower cost, and operational flexibility without betting the network on battery breakthroughs that remain just out of reach. Operations planners are already recalculating what is possible with a locomotive that can deliver its full power across long stretches of main line. For the first time, a single Class 99 can haul trains that previously demanded 2 diesel units, especially on electrified corridors like the East Coast and Midland main lines. This means longer trains, up to 800 meters in length, can run as a single consist, shifting more freight per path and reducing the number of locomotive moves required for each ton delivered. The impact extends beyond brute force. With higher acceleration and computer-managed suspension, the Class 99 can slot into timetables at speeds that once belonged only to passenger services. Freight no longer has to crawl at the margins of the network, waiting for a gap. Instead, planners can offer customers tighter delivery windows and more reliable transit times, making rail a stronger competitor to road haulage. A senior operations planner puts it simply: we are not just moving more wagons per train, we are getting access to better paths, and that changes the economics for everyone. The software-driven traction and ride control, tuned for each route, help unlock these gains in everyday service, translating engineering into commercial advantage. On a damp morning in 2024, a Class 99 running the East Coast Main Line flagged a subtle temperature spike, just 15 degrees above normal, on one of its axle bearings. The alert came not from a routine inspection, but from a predictive maintenance system drawing on data from over 120 onboard sensors. Within hours, a maintenance lead reviewed the anomaly, cross-checked vibration patterns, and scheduled a targeted repair at the next depot stop. The intervention happened before the bearing could fail, preventing an unscheduled breakdown that would have shut down the line for 4 hours and cost £25,000 in emergency repairs. For the maintenance team, the lesson was clear. Digital oversight isn't just about collecting data, it's about turning information into uptime. Instead of reacting to failures, the software allowed them to act in advance, keeping both the locomotive and the network moving. Operators face a familiar challenge: how to introduce a new locomotive without sidelining the investments already made in legacy fleets. The Class 99 addresses this with a straightforward promise: seamless coupling and multiple working with Britain's ubiquitous Class 66 and Class 70 diesels. Using the standard Delner-type coupling and conforming to UK multiple working protocols, a Class 99 can be paired with older units in a mixed consist, allowing traction commands and braking to synchronize across the lineup. A fleet strategist explains that this compatibility is not just technical, it is strategic insurance. Operators can phase in new units as budgets allow, running them alongside existing stock rather than forcing a costly, all-at-once replacement. This approach protects the value of current assets and offers a low-risk path to modernizing the fleet, smoothing the transition as the sector confronts tightening emissions rules and changing freight demands. Rebuilding a domestic heavy locomotive industry in Britain would come at a steep price. Industry strategists estimate a capital investment of £250 million to £400 million just to retool a single facility for modern assembly lines, testing tracks, and digital systems. Restarting production at scale would demand a skilled workforce of 800 to 1,000 engineers, machinists, and technicians at a time when much of that expertise has drifted to other sectors or retired altogether. These numbers stand in stark contrast to procurement decisions that now place a 40% weighting on operational flexibility rather than origin of manufacture. The calculus is blunt. Every pound spent reviving domestic capacity is weighed against the immediate need for proven, ready-to-run locomotives. As one strategist puts it, it's a question of sovereignty versus survival. Do we wait 4 years and pay more for a British build, or do we import now and keep the freight moving? The dilemma remains unresolved, its answer shaping not just supply chains, but the very definition of national capability. Britain's rail freight now stands at a technical crossroads. As the Class 99 enters service, its real test is not horsepower, but whether adaptability can outpace uncertainty. In a network shaped by compromise, the future belongs to infrastructure that bends without breaking. Subscribe to keep following the decisions shaping tomorrow's rails.